Hello, my name is Pratik. Uh, Let me show you how the way that I've built my project for the FIR. This is the hardware approach. So as you can see, I already have an existing project for the FIR hardware, which is named as FIR hardware underscore RTL.qpf. So let me just go ahead and load the file. Okay. The first and the foremost step that we have to do is build the QSys system. So let me just go ahead and open the QSys tool. The QSys is a tool that allows us to add components that can be later further on burnt onto the FPGA to make it work as a computer. As you can see, I already have a QSys system that has been built by me. So let me just go ahead and open it up to understand what components I'll be using. So yeah, let me discuss the components that I'm using in my QC system. I'm using the NIOS II, the economical version, which is set for its reset vector and exception vector at the on-chip memory base address. I'm using the on-chip memory, which is of 8192 bytes. I'm using the JTAG for the board, and I'm using a performance counter to calculate the number of cycles that will be required by the hardware approach to give me the output. Over here you can see that I've added a component as my FIR. So let me just go ahead and show you my FIR component. So these are the files that I'm adding for my FIR. I have an accumulator, a multiplier, and a flip-flop, and a top module which has the logic for the rounding and the saturation, which is also defined as the top level entity. The signals that I'll be using are defined over here, which is clock, reset, address of 16 bits, read and write signals, a read data which is output 16 bits, and a write data which is input 16 bits. This is the top level address that I'll be getting, which will communicate my bus NIOS busmaster with my Avalon slave busmaster. So as you can see over here, I have a clock interface, a reset interface, and an Avalon memory map slave interface. Over here you can see that the signals are buffered as address, read, write, read data, and write data. So let me just go ahead and save this and exit. This is how the top module will be instantiated for the QC system. So let me just go ahead and hit generate. So once the system is generated by QSys, when I upload the IP variation file onto my quarters, the system components will be converted to Verilog files, and I can actually compile and analyze the Verilog files for any errors, and that will be my actual hardware in quarters. So let me just go ahead and refresh my files. This is the existing QIP that I have, so let me just add it again. Okay, so you can see over here from the drop down approach that I have all my submodules instantiated and as Verilog files. One other thing that we need to take into consideration is the assignment of the pins. Since the only pin that we will be using over here is the clock, so the clock is located at a value pin L1 on the DE1 board, which is at a 3.3 low voltage TTL standard. So let me just go ahead and hit compile to compile the code. So once the code is compiled for no errors, we can actually burn the code onto the FPGA kit. So the FPGA kit will have the system ready on it, and we can use the NIOS II system to communicate with the hardware that we have put it onto the board. So let's wait for the compilation to complete. Okay, so the compilation was successful with no errors. So let me open up the programmer, which will help me program the board. So as my hardware is set up as the USB blaster, which I'm using to connect the DE1 board. So let me just go ahead and hit start. Okay, the programmer was able to successfully program the code onto the FPGA board. Now my FPGA is ready with the hardware that I've added on, and let me just open up my software build tool to program the NIOS II. So as you can see over here, it already locates the path of the workspace that I have built. I'll just go ahead and hit OK, which will load my SBT, and it will also load the C program for the FIR filter. So this is my C program for the FIR filter. So first and foremost, let me cross-check the base address for the hardware components that we'll be using. So the two hardware components that we'll be using are the FIR filter and the performance counter. So let me just go ahead and check the base address for the FIR filter. So the FIR is at a base 0, and the performance counter is at a base 25,000. So as you can see on my code, I have set my performance counter base as 25,000 and the FIR base as 0. So let me run the code for the first string of inputs. I'm using the performance counter before giving my stimulus to the FIR, and I'm ending it right after it, and I'm using the inbuilt function to get the performance. So since we've generated the QC system again, I'll have to generate the board support package for the NIOS II. Once that is done, I can just clean the project and run it as NIOS II hardware. So the build was successful. I'll just say yes to save the C program. It was able to verify the base address and start the processor. Okay, so for the first string of inputs, for the data and the coefficient, my output is -34 with almost about 10,000 clock cycles. As you will see later via the software approach, this is almost 10 times faster than what we see when we actually build the system via a software approach. So let me go ahead and run the program again for the second set of inputs. Just save the file this time, clean the project, and run it as NIOS II hardware. Okay, so it's trying to communicate with the target device, and there we go. The FIR output for the second string of inputs is -2229. This is because the FIR over here is a hardware which doesn't have an external reset, and since I have an accumulator in my hardware, so the first string of inputs gave me a value of -34, which was accumulated with my output of the second value, which is supposed to be -2195, which gave me an output of -2229 with almost the same number of clock cycles. So that's about it for the hardware approach. Thanks for watching.